we can discuss this offline. Thanks again. The next speaker is Michael Murphy, and he's talking about recent advances in the use of GNSS-RO observations in NWP at NASA's GMAO.
Great. And everyone can see the screen there properly?
Yes, we can. We can hear you as well.
Great. So yeah, I'm here representing, I'm actually here, remotely. Unfortunately, I wasn't able to make it for family reasons. But I'm here listening to all the talks and excited to be presenting again at IROG. So yeah, I'm gonna be talking about what we've been up to at NASA's Global Modeling and Assimilation Office concerning radio occultation observations. And I'd like to acknowledge the team listed here at GMAO that I'm working with, as well as Rick Anthes from UCAR Cosmic and the whole ROMEX team. So at GMAO, we've got both operational numerical weather prediction and which uses radio occultation, including commercial RO. And we have reanalysis projects going on. We're currently working on the MERA 21C product. This is the bridge between the current MERA 2 and the further in the future MERA 3 product. So this MERA 21C is just going to cover the satellite era, i.e. the 21st century. And the cool thing about that product is we're including this high volume commercial RO from the CSDA archive. I have a plot of that on the right here. And in blue is Spire, this time series. You can see blue, and later in the time series, you can see we have this really high volume of Spire radio occultation profiles that we're going to be including in the MERA 21C product. But for this presentation, I'm not going to focus on reanalysis or so much operational NWP, but more the research we've been doing. And that includes two main things: the evaluation of different RO observation error or uncertainty models and QC methods in GEOS, as well as our progress and some very initial results from GMAO's model runs for the ROMEX experiment. So we'll start with the observation uncertainty model in QC. So in data assimilation, we're trying to minimize the following cost function. And the term that's of interest here is the observation error. This is the R matrix. That's where the observation uncertainties are incorporated in. So the larger the uncertainty assigned to a given observation, the less closely the model analysis produced by the DA system will draw towards that given observation. And an observation uncertainty model is the method of estimating the uncertainty used in the above cost function. So the uncertainty model is kind of set aside from this cost function. It's just used to estimate what goes into the R matrix. Another very important piece of this is the quality control method that's used, because that really affects what observations are actually used in the system. So the current method used at GMAO is very similar to what was described in the previous talk that's used at NCEP. Some key differences are that at GMAO is how commercial RO is treated. So commercial RO is inflated by a factor of 2. It's observation errors. And there's also different cutoffs that are given to different constellations using this system. And I made a plot here. If we look in terms of radians here at the observation error with respect to impact height, you can see for different constellations, we have Spire in blue, Cosmic 2, purple, and MEDOP in green. You can see they have different vertical profiles of observation uncertainties. And you can see I've highlighted the cutoffs here. So the same as what you saw in the previous talk with NCEP, we're cutting off MEDOP at 8 kilometers using this method. And for Spire, we differ from what was described doing at NCEP. We're also cutting off Spire below 5 kilometers. This applies to all commercial, or I'm showing Spire as an example. And you can see that cutoff at 45 kilometer impact height as well for commercial RO in this system. This is this method that's currently used at GMAO. So we've been exploring using just a much, the ECMWF's model, which is much more simple. I've made a plot of it here. So it's dependent only on impact height, and it's independent of mission or latitude or any of those things. And you can see that it has a linear, it starts at 20% at 0 impact height and decreases linearly to 10 kilometers impact height, after which it's constant 1.25% with a lower floor of 3 microradians, which results in this curve you see in the upper levels. And there's no cutoffs, depending on what mission it is, or there's no inflation of errors that are going on as there was in the other method. So a very different method, and we wanted to the real motivation here is to move towards using more of the observations, right? Not discarding so many of the observations. So we're trying out this ECMWF observer method and seeing what the impact is. And you can see here in the this is the innovations. We have the mean of the innovations on the left panel. Middle is the standard deviation, and then the actual count. The units are a bit off there, but you're getting an idea of the count of observations retained for Spire over here on the left. And yeah, what you see is you get more, you see these cutoffs, right? So the control in red is showing these cutoffs I was just mentioning for Spire. So we keep the observations here in the lower and upper levels using the experiment, and you can see that we have larger values of standard deviation and also bias in the lowest levels because we're retaining these observations. Similar case for Cosmic 2, except you're not having the cutoffs in GMAO's current method being used. So what's the effect of these two different methods? So here's the monthly mean for temperature on the left, U and V winds in the center and right, and just taking the experiment minus the control, and you can see we're getting very large differences between the two, especially above 35 kilometers. And so in order to kind of figure out, which experiments performing better, we validated against 2 microwave instruments, AMSU-A and ATMS, and you can see that actually using this using this new method of observation here in QC is resulting in a degraded performance for the analysis. So yeah, just doing the fit to the observation. So we're just comparing the analysis, not very short-term forecast. So essentially the analysis, yeah. So yeah, this raises some questions. This is still ongoing work. We're trying to figure out if this is related to the QC that's going on, or is related to the observation error model itself. We need to tease those two things out, do them separately. But yeah, so far just showing some preliminary results of what we found with these evaluations. Next, I'll give a some brief progress and some very recent initial results we got from ROMEX for the ROMEX experiments. So ROMEX seeks to answer what is the impact of greatly increased volume of our observations on NWP forecast. That's the central question with ROMEX. And GMAO is one of the many operational centers participating in this using our GEOS model described here. And yeah, and we are using the standard observation error model that I was describing in the previous slides. We're not using any changes to that. We're sticking with what's used in operations. And so far we've completed 1 month of the 3-month ROMEX period. So I'm going to be showing results from just that first month. And here's an example in the table for just a single day of how many RO how many RO profiles we have from these various missions. And you can see that the control we have about 8,000 profiles for this day, whereas in the ROMEX experiment, we have almost 35,000. So many, many more RO profiles. So just looking at the innovations here, the O-B statistics, I'm just plotting. So yeah, this is the count on the left. You can see the difference in count between commercial in blue and non-commercial missions, public missions in red. So many more occultations. You can see the cutoffs that we were talking about caused by the QC method. We're cutting all these commercial are off at 45 kilometers. We're cutting them all off at 5 kilometers. So only between 45 and 5 kilometers impact height do we actually use these observations. And you can see that in the extratropics here, as well as in the tropics, similar biases and similar standard deviations as well for these two groupings of missions, commercial versus public. So this suggests good agreement between these missions, and we have good quality in the commercial RO. And this is just an example from a single day within the month that we're evaluating. So now we're doing this fit to the observations again. This time we're seeing, AMSUA on the left and ATMS on the Yep. Yeah, and you can see in this case, we are getting improvement to the forecast in the experiment, the ROMEX experiment, which has all those extra RO observations. Yeah, in addition to that, we also looked into the FSOI statistics from this, just preliminarily. So FSOI is forecast sensitivity-based observation impacts. It utilizes the DA system to get the impact of any observation or group of observations. And this is based on short-term forecasts, usually 24 hours, in this case, 24 hours. So there's a lot of applications we could do with this, but just wanted to show briefly here that on the top, we have the ROMEX control, in the bottom, the ROMEX experiment, and I'm highlighting GNSS-RO here, all of them combined together, right? So we're seeing a larger fractional impact whenever we include all these extra ROMEX observations. And you can see that even GNSS-RO is it's increasing in its ranking here. If you count 1, 2, 3, yeah, it's doing a little bit better in the ROMEX experiment. So just kind of a ballpark, we are seeing improvements, at least in the short-term forecast. Less so in the tropics here. This is the tropics, and it's not as obvious an improvement there, just eyeballing it. And we haven't gone so far as looking at the forecast. That's the next step, and also calculating statistics that'll be compared with the rest of the centers in the ROMEX experiment participating. But yeah, just wanted to give some very brief results. There'll be more talk about ROMEX later in IROG here. So yeah, in summary, at GMAO, we're investigating different methods for observation uncertainties and QC methods for RO. Our goal is to use more of the RO observations in the DA system than are currently used. Initial results were suggesting that just going straight to the DCMWF model was not improving the forecast. And we're going to investigate teasing out just the error model versus just the QC criteria, how changing just those things alone might affect it. Yeah, and finally for ROMEX, GMAO's finding so far initial results are encouraging. Yeah, commercial obs seem to be of good quality, and we're getting improvements to the analysis and short-term forecasts. The preliminary analysis suggests. Okay, and with that, I'll take questions.
Thank you. We have time for one question. Rick?
Hi, Michael. Nice talk. Did you do some verification against, say, radiosondes or ERA5 or ECMWF analyses in addition to the AMSU?
For which part of the analysis?
I think it was ROMEX. You showed you showed both. Right. Both parts, but for ROMEX, you showed verification generally better against AMSU.
Right. Yeah.
But did you compare to either some other analysis or to radiosondes?
Yeah, these are results really just hot off the press, and we didn't, I don't have I didn't do the radiosonde comparison
Okay.
yet. Went straight to AMSU-A and ATMS. Yeah.
Let's
lot
thank
of
Mike. Sorry.
Oh yeah, a lot of work to do still there with evaluating the ROMAS experiments.
All right, let's thank Michael again. The next speaker is Hailing Zhang. She's